Hello. In the last lecture, we looked at real-time uniprocessor scheduling strategies used in embedded systems. In this lecture, we will look at real-time multiprocessor scheduling approaches. So, multiprocessor scheduling attempts to solve the problem of resource contention among programs running on different processing elements. So, we used uniprocessor scheduling to solve the problem of contention among tasks running on the same processor. Now, if you have multiple processors and there are tasks that must be executed on a set of more than one processor, then you have to use multiprocessor scheduling strategies. So, therefore, it attempts to solve the problem of resource contention among programs or tasks running on a set of more than one processing elements. And there are two primary approaches towards multiprocessor scheduling. The first is global scheduling, which treats processor as a pooled resource. So, we do not consider separate processors. We consider all processors together as a single pooled unified resource and assign tasks to processors on demand. So, the same task can be assigned to different processors as and when required based on demand, with migrations being required when we have to transfer a task from one processor to another. But we will see all the processors together as a single resource against partition scheduling, which is the other type, where we permanently assign each task to a single processor and which are never allowed to switch between processors. So, the tasks are not allowed to switch between processors. Okay. So, once there is a allocation phase in partition scheduling, there is an allocation phase where you allocate each task to a distinct processor and you run that task on that processor and never migrate it for the entire duration of its lifetime. Between these two approaches, you also have something called hybrid scheduling, which is a trade-off between fully global and partitioned approaches. This allows restricted migrations, meaning that, for example, you can have each job of a task to execute on a single processor, but different jobs can execute on different processors. For example, let us say you have a task consisting of a sequence of jobs J1, J2, J3, J4. J1 can run in processor 1, J2 can run in processor 2, J3 can again run in processor 1, J4 can run in processor 3, likewise. So, we have allowed restricted migration. So, you are allowing job level migrations and therefore, it is not fully global scheduling and it is not fully partition scheduling. It is not fully partition scheduling because you are allowing migrations, but it is not fully global scheduling because you are restricting migration within a job. So, the job could be arbitrarily long and for the entire lifetime of the job, over the entire execution time of the job, it has to execute on a single processor. So, therefore, it is not absolutely global scheduling, not absolutely partition scheduling, something in between, hence it is called hybrid scheduling. Now, we look at partition scheduling in a bit more detail. So, partition scheduling, it partitions tasks so that each task always runs on the same processor as we said. And so, what we do is we assign tasks to processors first using a strategy called bin packing. So, here bin means processors. So, each processor is a separate bin of a certain capacity, and if you have homogeneous processors, you can always assume that each processor is of unit capacity 1, and you assign tasks which are individually of size equal to its utilization. So, we are saying that let us say you have a task of period 4 and to be executed for and with an execution time of 2. Its period is 4 and its execution time is 2. So, the utilization of the task E by P is 2 by 4, which is half. So, we know that if the capacity of the processor is 1, I am assigning a task of size half onto this processor. So, here this processor will be called bin and we have to pack tasks onto each of these bins and hence it is called bin packing. Now, we have separate run queues. So, this one is processor 1, this one is processor 2, processor 3 and processor 4. You have 4 processors and you have 4 separate run queues for each of them, 4 separate run queues, and you have assigned the tasks to be allocated to each run queue or each processor. So, these are the tasks which are assigned to processor 1. Similarly, these are the set of tasks, each one of them being a separate task being assigned to processor 2. Likewise, so what is the advantage of partitioning? The one big advantage of partitioning is that once you have allocated the task to separate processors, then you can use well known simple uniprocessor scheduling algorithms like EDF, RMA or LLF. LLF is least laxity first, which we have not studied, but it is a derivative of EDF where you allow priorities of the jobs within the jobs to change. So, the jobs again will be divided into subtasks, where each subtask can be executed within the time slots assigned by the operating system, and different subtasks within a job can have different priorities. That is LLF, we did not discuss it. However, it is also an algorithm that is used in uniprocessor systems. So, well known uniprocessor algorithms like RMA, EDF, LLF can be used within each processor once you divide the task into the individual processors. This is why this partitioning approach is many a times used. And also the overheads are also less, because once you assign the task, you do not need to migrate tasks from one processor to another. Migration is a high overhead process, as we will see in time in a few slides from now. Now, partitioning, as we told, is the assignment of tasks to processors, but this bin packing strategy, the optimal strategy for bin packing is an NP hard problem. So, it takes exponential amount of time with respect to the number of tasks, and therefore, when the number of tasks and processors in the system increase, the partitioning process becomes very complex and time consuming. So, therefore, people typically use heuristics to solve the bin packing problem, and there are a few very well known heuristics like first fit, best fit, worst fit and first fit decreasing. In the first fit, what do you do is, suppose you are given a set of processors, you put the task in the first processor and you name the processors, say P1, P2, P3 likewise, and you start assigning tasks. So, you have a set of tasks, you start assigning tasks from P1, P2, P3 and what do you do is, you take the next task and put it in the first processor which has enough capacity to hold it, hence first fit. So, you start allocation from an assigned processor P1, then P2, then P3, you maintain this order for consideration of the task for allocation, you always maintain the same order. And where do you put the tasks? Onto the first processor when searching in this order that has enough capacity to hold the next task. Okay. Best fit, on the other hand, what does it do? It takes the processors and finds out that processor among the set of all processors which has the least capacity, but can hold this job, which has the least remaining capacity, but that capacity is sufficient to hold the next job. So, it is the best fit. It is called best fit because it does not allocate to the first processor that can hold it. The first processor can have a large capacity remaining or may not have any capacity remaining, but what does best fit do? It tries to find that processor which just has sufficient capacity to hold the task. Any other processor which has more this processor, this best fit processor, that processor will have a higher priority for this job than any other processor which has higher remaining capacity, and no other processor with lower remaining capacity can hold this job, right. So, this is what is best fit. Worst fit, on the other hand, what does it do? It places the next task onto the processor which has the highest remaining capacity. So, hence worst fit. All these heuristics are used. First fit decreasing. In first fit decreasing, what do? We take the task and first sort them from the highest size to the lowest size, and then we apply first fit, hence first fit decreasing. Now, we will look at first fit decreasing in a bit more detail with an example. Let us now understand the first fit decreasing algorithm with an example. Let us assume that we have a set of these 9 tasks. The first task having an utilization 2 by 3, second task having an utilization 1 by 6, third task having an utilization 1/3 and so on, to be scheduled on a set of these 6 processors. Okay. These are all unit capacity, 6 unit capacity processors, and we now must partition the task set first before scheduling, because we are doing a partition scheduling and we are using bin packing for the partitioning process. So, now we have to partition these 9 tasks onto these 6 processors, okay, using first fit decreasing. Now, first fit decreasing says that we need to first sort the tasks based on their utilizations. So, after sorting, we get this sorted sequence of tasks from the largest task to the smallest task, and after sorting we need to apply the first fit algorithm. Thus, we take the first task and put on the first processor that can hold it. But before going to do that, we will just for convenience change these tasks, these fractional utilizations into integers. We will scale these tasks so that each of this becomes an integer, which essentially means that what we are going to do is that we will multiply each of these utilizations by 6, and then the capacity of the processors instead of 1 will now become 6 after we scale these tasks. So, after scaling, what happens? The weights we have now scaled, and therefore, the task 1, the weight which was 1 has become 6, the weight which was 5 by 6 have become 5, the weight which was 2/3 has become 4, and likewise. So, we have changed all the task weights to integer values, and therefore, the capacity of the processor have now become 6. Each processor is now 6. So, now we will apply first fit on this. So, therefore, the capacity of the first processor is 6 and the task size is also 6. So, the first processor has been completely filled. So, now we have the second task, we try it on the first processor, but we do not have enough capacity on the first processor. So, we go on to the next processor, and therefore, the next processor has enough space, and we put the next task onto processor B. We take the third task, we try the first processor, we try the second processor, cannot hold it. Why? The second processor also cannot hold it, because the processor has a capacity of 6 and 5 plus 4 equals to 9. So, the second processor does not have enough capacity to hold both the tasks, and therefore, it will be allocated to the third processor. Similarly, the third one will try to go on, try to put it onto the processors in the order one by one, and then finally put it in its final place. Okay. So, we see that the processor D can hold both these 3 together. Why? Because the capacity of this processor D is 6, all the processors have capacity 6, and the summation of the weights of these 2 tasks is 3 plus 3, which is 6, and hence we can put both the tasks onto the same processor. The next 3 cannot be put here, and hence it will go to E. The next 2, okay, this can hold it. Why? Because C is sufficient to hold this 2, because previously 4 was previously the task with weight 4 was in C, and it still has 2 of spare capacity, and that within that spare capacity we can put the next task whose size is 2, and therefore, this for the next task we can again will see that it cannot be put in any of the processors, and it has to go to E. Similarly, lastly, for the last task it must be put on to the second processor. Now, we have packed all the tasks into 5 bins. So, this is first fit decreasing. Similarly, we can have best fit decreasing, in which again we will first sort the tasks and then put the next task onto the processor which has the least remaining capacity, but that capacity is sufficient to hold the next task. Okay. So, in best fit decreasing we will first sort the task and put this will consider the task in order of from the largest to the smallest size, and we will put the next task into the processor that has just the sufficient capacity to hold the task. That will be best fit decreasing. In worst fit decreasing, we will again sort the task and take the from largest to smallest and take the next task and put the next task into the processor which has the highest remaining capacity, that is worst fit decreasing. Okay. So, all these types of packing strategies are used depending on the situations. Now, once such a packing is done, we have packed. So, we have packed into 5 processors and the one processor still is there which is spare, and if further tasks come in we may need to put it into that processor, but currently this processor will be idle or will be kept off. And then now on each of these processors we will apply uniprocessor scheduling strategies like EDF RMA to schedule the tasks in each of these processors. Now, we come to global scheduling. In global scheduling, as we said, we consider the processors as a single resource pool. So, therefore, we have a single queue. So, this is the single resource pool consisting of all the processors, and instead of separate run queues we now have one single run queue, and then there has to be a dispatcher which will find out to which processor each task each task or job of the task or the next subtask of the task given will be put. Okay. So, the important difference here is that the task can migrate among processors. Now, partition scheduling, although is sometimes used because we can use well known uniprocessor scheduling algorithms and that migration overheads are also low, but partition scheduling often produce very poor resource utilizations. For example, we will take this case where we have 2 processors CPU 1 and CPU 2 and we have 3 tasks, each of whose utilization is 2 by 3. Okay. So, 2 units of work are to be done every 3 time units. So, its period is 3 and its execution requirement within this period 3 is 2. So, its utilization U is equal to 2 by 3. So, we have 3 tasks like this. When we are partitioning, we put the first task onto CPU 1, we put the second task onto CPU 2, but we cannot put the third task into any of these processors, because we only have this task has a weight of 2 by 3 and here you have 1 by 3 remaining and here also you have 1 by 3 remaining. 2 by 3 has been used by task 2 on CPU 2, 2 by 3 has been used by task 1 on CPU 1. So, you have 1 by 3 spare capacity on processor 1, 1 by 3 spare capacity on processor 2. So, the total remaining processor capacity though is 2 by 3, you cannot use this spare capacity to hold task 3, because none of the individual processors have enough capacity to hold this task. So, what can you do? You can just break this task into 2 subtasks, into 2 chunks, into 2 separate chunks of size 1 by 3 each. So, the first chunk is task 3 by, so the first chunk is 3A, which will be scheduled between 0 and 1 here, and the second chunk is 3B, which will be scheduled here. So, why have we done this? So that if we do not do this, we have to, if we schedule task, we cannot schedule task 3B and task 3A here, right? We cannot schedule 3A here. This is not possible. Why? Because otherwise these are 2 separate, means otherwise this is a sequential process, right? So, the first part has to end and only can the second part start. The 2 parts cannot execute in parallel. I have a single program code, let us say, I have divided into 2 parts, but I cannot execute this until I finish this. So, these two executions cannot be overlapped, these two separate executions cannot be overlapped. Hence, task 3A and task 3B cannot be executed at the same time on two processors, and hence we have put task 3A at the beginning and task 3B at the end here. However, this scheme allows us to schedule to appropriately schedule the third task. Partition scheme could not do it. Now, in a global scheme, by allowing a migration, we can allocate these 3 tasks. We divide the task into 2 parts. We execute the first part in CPU 2, then we migrate the task from CPU 2 to CPU 1. So, the code, if required, along with the intermediate data of the task, is migrated from CPU 2 to CPU 1, and then the next part of this task is executed on CPU 1 after its completion on CPU 2. So, by incurring a migration and by dividing the tasks themselves, we will be able to successfully execute this task, and hence global schedulers succeed on multiprocessors. So, if we just see the pros and cons of global scheduling versus partition scheduling, we see that global scheduling has no restriction on migrations and it allows good resource utilization, as we saw, and in the last case, in the last slide, we saw that it allows 100% utilization of the processors. It is bad in terms of high migration cost and also cache misses. Why? Because once you execute a task, once you allow migrations, what happens is that the cache corresponding to what was executing before is flushed. So, when you bring in, suppose you break a task and you bring in break a task and into 2 parts, and you take the first part, execute on some processor, and then you migrate it to a second processor and you execute over there. So, what happens is that in the second processor, the cache is cold with respect to this task. The data corresponding to this task does not reside in the second processor's cache, and therefore, initially there will be a lot of cache misses. And in general, when migrations are allowed, such cold misses will occur again and again, and therefore, this will incur a high cost, high migration cost. Partition scheduling, on the other hand, are strict in terms of not allowing migrations, and therefore, it is good because it has no migration cost, and therefore, it is high in terms of cache efficiency. Cache misses are low, but it is bad in terms of low resource utilization, as we saw in the last case. 1/3 of the processor of each of the processor could not be used. So, the processor utilization for that particular case was 66%. Why? Because the total was 2 and we could only execute 2 tasks of weight 2 by 3. The third task of weight 2 by 3 could not be executed. So, 1/3 of the total system capacity was wasted, and hence the utilization was around 66.6%. In general, if we restrict more, the runtime overhead is reduced. So, if we are more and more partitioned, if we go towards partitioning, runtime overheads are reduced, and however, the schedulability or the resource utilization bound is also reduced. So, based on this classification on migration, we can have different classes of scheduling algorithms. Firstly, we have no migration, the task cannot migrate and the jobs cannot migrate. We can have this is the case which shows that, so these are 2 distinct jobs and the jobs have distinct subtasks. Each of these boxes are subtasks of the same job. So, the job consists here of 3 subtasks, and all the subtasks of all the jobs of this task must execute on the same processor P1, and therefore, it is a completely partitioned approach. In the restricted migration case, the tasks can migrate, but the jobs themselves cannot migrate. So, all subtasks of the same job must remain on the same processor. However, 2 separate jobs can be executed on 2 separate processors. And we can also have full migration, where the task can migrate, the jobs can also migrate. So, The first subtask of the first job executes in P1, the second subtask of job 1 executes in P2, the third subtask of job 1 executes in P1 again, the first subtask of job 2 executes in P2, the second subtask of job 2 executes in P1, third subtask of job 2 executes again in P1. So, this is a case for full migration. So, when we are doing a global scheduling, it allows a lot of task migrations, which leads to cache misses, and this cache misses can become harmful, especially when the CPUs are connected via bus or network, that is, it is a distributed system, and therefore, taking the task from one processor to the other is costly. In a distributed system, you do not have a shared cache. So hence, the code of the task as well as the data cannot be stored in the shared cache, so that it can be easily made available to another processor, and hence the entire code and data must be transferred over bus to another processor. So, therefore, these such task migrations are harmful when CPUs are connected via bus or network. When each CPU has its own memory, it still is much more harmful if the CPU, if the memory itself, not even cache, but the memory itself is separated. So, therefore, you have to transfer the whole, it is not even in memory. So, you have to transfer the whole task from the memory of one processor to the memory of the other processor. In the first case, if the memory is shared, you at least do not need to do a bus transfer, it is there at least there in the shared memory. But if the memory is also separate, then you need to do a complete bus transfer of both the code as well as the data of the task from one processor to another. So, and if the shared global memory, even if you have a global memory, if the shared global memory is not sufficient to hold all states of the task, then also such task migrations or cache misses become harmful in terms of the overheads it has. And it is not that harmful for CPU cores on a single chip. For CPU cores on a single chip, even if you have task migrations, it is not that harmful, because CPUs are connected may be connected via high speed interconnection on chip network. Therefore, the task misses are not that time consuming. So, the transfer of both code and data is not that time consuming, and hence the overheads are less. CPUs share a large global memories and caches, and hence the transfer has less cost. Therefore, whenever we have lower migration costs, we can use a global approach. We can go towards a global approach when the migration costs are less. However, when the migration costs are more, as in a loosely coupled distributed setting, then we must go towards more partitioned approaches. Greedy algorithms generally fail on multiprocessors. Why? At each scheduling point, a greedy algorithm will regularly select the m best jobs to run. For example, we will select the m best jobs in the earliest deadline first order. So, we have a multiprocessor, we have a set of m processors, we have a multiprocessor system consisting of m processors. A greedy algorithm, even if it is a global algorithm, what will it do? The greedy scheduling algorithm will choose the m best tasks and allocate onto m processors. For example, if we have an earliest deadline first, we will take the m best jobs in terms of their earliest deadlines. These tasks will have the earliest deadlines and allocate onto m processors in order. Okay. But this strategy fails on multiprocessors, and we will see why. So, that is why, although EDF is an optimal algorithm, as we have seen on a single processor, it is not optimal on a multiprocessor system. So, greedy approaches generally fail on multiprocessors. Now, let us take an example to see why this happens. Let us say we have 3 tasks to be scheduled on 2 processors. The 3 tasks have, task 1 has an execution requirement of 9 to be scheduled within a period of 10. So, it has an utilization of 9 by 10. The second task also has an utilization of 9 by 10. So, task 2 has a work of 9, or execution requirement of 9 to be completed within a period of 10, and the third task has an utilization of 8 by 40, okay, or 1 by 5. So, the third task has an utilization of 1 by 5. It has an execution requirement of 8 to be completed within a period of 40. If we add these utilizations, we see that 9 by 10 plus 9 by 10 plus 2 by 10, which is equals to 2. So, the total utilization is 2, and therefore, the total capacity of the system is also 2 unit capacity processors. So, in the ideal case, we should be able to schedule on these 2 processors. We should be able to schedule these 3 tasks feasibly onto these 2 processors. However, we will see that if we use greedy strategies like EDF, it is not possible to do so. So, what happens at time 0? At time 0, tasks T1 and T2 are the obvious greedy choices. Why? Task T1 has a deadline of 10, task T2 also has a deadline of 10, task T3 has a deadline of 40. So, these two have task 1 and task 2 are the ones with the earliest deadlines and are scheduled at time 0. And if we see that their jobs complete at time 9, at time 9 only the third task is left, and it is executed, let us say, on CPU 2 for 1 time unit, and therefore, at 10 7 time units of work for task 3 is still left. 7 time units of work is left for T3 at 10. Okay. And then at 10 the next jobs of T1 and T2 arrive again. So, again T1 and T2 are the greedy choices, the best greedy choices, and T3 does not get a chance. T3 again gets a chance at 19, okay, because at 19 both T1 and T2 will finish at 19, and then between 19 to 20 in that time slot T1 will execute for 1 slot again, and then again it will again get another chance at 29 and another chance at 39. But then by 40 we understand that T3 will only complete 4 units of work, but it needs to complete 8 units of work. If we see why this happened, we see that every 10 time units we have to keep the CPU idle for 1 time unit. We cannot schedule anything here in this place. Why? Because we have nothing to execute. T3 is executing on the other processor, and it cannot execute at the same time on 2 processors. We cannot have overlapped executions, and therefore, due to these free slots, these idle slots of the CPU, every 10 time units one idle slot of the CPU, this makes this task 3 miss its deadline at 40. So, however, what happens, there is something important that happens at 8 which we must be missing here. So, even at 8 what happens, the tasks T1 and T2 are the only reasonable greedy choices. Why? Because at 8 we see that if you see even at 8 task T1 has a deadline of 10, task T2 has a deadline of 10, while task T3 has a deadline of 40, and therefore, at 8 also we schedule both T1 and T2, and we don't execute T3 up to this unit, this 9. Yet if task T3 task T3 isn't started by 8. So, why did we talk about this 8? Why was 8 so important? If task T3 is not started by 8, the resultant idle time here eventually causes a deadline miss. So, if task 3 was started at 8, what would happen? Suppose we executed this blue task, which is T2, up to 8, and then we executed task T3 for these 2 time units here, then what would happen? We could migrate this task from here to here, this task T2, and one remaining slot of execution of T2 could be executed here. Okay. So, this place T2 could have executed, but then for that we need to understand that at 8 we have something important. At 8 we need to allocate T3, otherwise ultimately at 40 it will miss deadline. That has to be understood. So, how do we make the system understand this? So, how can we see this critical event at 8 is the question. So, what can we do? We can subdivide task 3 with a period of 10. Now, if we subdivide task 3 with a period of 10, we see that every period of 10 it needs to do a work of 2 units. So, within 10 if it will do it must do 2 units of work, within 20 it must do 2 units of work, within 30 it must do 2 units of work, and within 30 to 40 also it must do 2 units of work in order to complete all its 8 units of required execution. Then what happens? We see that then we can, if we do this proportional division of the workload of task T3 into 4 chunks of 2 units each for every 10 time units of work, this proportioned division of work for T3 makes it possible to view this important event at 8. We see that at 8 task 1 has 1 unit of work remaining, task 1 has 1 unit of work remaining, task 2 also has 1 unit of work remaining, but task 3 has 2 units of work remaining. So, suddenly at 8 T3 becomes more important than T1 and T2, because it has 2 units of task remaining to be completed before 10. T1 has 1 unit of work remaining to be completed before 10. T2 also has 1 unit of this happens at 8. At 8 T1 has 1 unit of work remaining to be completed within 10. T2 also has 1 unit of work remaining to be completed within 10, but T3 has 2 units of work remaining to be completed within 10. So, in this sense T3 becomes more important than T1 and T2 at 8, and hence T2 for in this case T2 is preempted and T3 is allowed to execute onto CPU 2, right. And then you have 1 unit of work remaining which can be executed in CPU 1 after T1 completes its execution at 9 by incurring this migration. Hence, proportioned algorithms which does what? Which proportionately divides the workload with respect to deadlines of tasks succeed in multiprocessor systems. So, if we can determine, if we can find what are the deadlines for different tasks in the system, and by all these deadlines we proportionately execute the workloads of tasks, we will succeed on multiprocessors. So, this is the takeaway here, and so now T3 has a 0 laxity event at 8. So, 0 laxity event meaning that it has 2 units of work to be completed within 10. So, amount of work remaining is 2, amount of time remaining is also 2. So, laxity is 0. So, now task 3 has a 0 laxity event at 8, and because the laxity is 0, task T3 becomes more important than task T1 and T2, because they still have a laxity of 1 at 8, and hence we allocate T3, and therefore all the 3 tasks can meet their deadlines using this approach.